So I don't have the exams grade yet, but I will this afternoon. We will be starting a topic here that Brittany will be teaching.
Mm-hmm.
Yeah, right.
I already took this class.
You're seriously having chocolate on tater tots?
Yes. Well, the tater tots happen to be on top of the pancake waffle when I put it on. So.
Bottom line, yeah.
Mm-hmm.
Chocolate, it might be good. I've not tried it. Okay, so we're starting in astronomy. And unlike when Brittany took the class, we won't be singing any songs.
What? Why not? That's too sad.
Because we have a whole semester to cover astronomy in Brittany's class, whereas in this class we have the last 2 weeks of the semester, actually the last week roughly of the semester, because then we have review and final exam coming up. So let's get right into it. The solar system is the system of things that go around Sol, right? Sol is the name for our sun. And so the solar system are things that go around Sol. So we have the sun at the center, Sol or Helios, there's a couple names for it. That dominates our solar system. It's virtually all of the mass in our solar system. Now notice I did not say it's all the mass. It's virtually all the mass. If you compare the mass of all the planets, it's a small fraction of the mass of the sun. Then we have the systems of planets. How many planets do we have in our solar system?
9.
It was 9 when Brittany took astronomy. Yeah. But it's 8 now. And there's a good reason why it's 8. So we'll get into that today. So we have 8 planets. And many... Excuse me?
I thought they rediscovered that.
Rediscovered it?
We saw it, whatever. I don't know. Never mind. Sorry.
That was a April Fool's joke. Okay. All of the planets except for the inner 2 have moons. And so we'll learn a little about the moons as well. Then we have asteroids. Asteroids are rocks. They may be rocky rocks like silicate rocks, or they may be metal rocks like iron rocks that are out there orbiting about. And finally, we have comets. Comets are things like Pluto that are like ice and rock mixed together. And so Pluto is now classified as the type of object that comets are made out of. And it's not the biggest one of those objects. And that's part of the reason that Pluto got demoted. But, well, we'll get into that. So the planets are divided into the inner planets and the outer planets. The inner planets are all rocky. That is, they're all big rocks. And so you have Mercury, Venus, Earth, and Mars. Of these, the largest one is the third rock from the sun. Yes. At least one person remembers the TV show.
I was probably the only one.
Earth is the third rock, the first rock Mercury, second Venus, the fourth Mars. All of these are similar because they have a similar density. The densities of these are all in the ballpark of 3 to 5.5 grams per centimeter cubed. Astronomers will actually calculate the uncompressed density. That is the density that these planets would have if gravity wasn't compressing it. And that comes out even much closer. So they're made out of very similar materials. And then we go to the outer planets, Jupiter, Saturn, Uranus, and Neptune. Now, if you look in this picture, I believe the planets are to scale. I'm not sure if the sun is to scale. Obviously, the distances are not to scale. But you see that these outer planets are much bigger than the inner planets. But the outer planets have a lot of gas in them. Now, gas is low-density material. In fact, Saturn is less dense than water. So those are lower density, but much bigger and more massive. At the cores of each one of these outer planets is a rock. And I believe all of those rocks are bigger than all of the rocks in the inner planets. So it's not like they don't have a big rock. It's just they have a lot of gas outside. Now, a big question would be, why the separation? Why are the things that are farther from the sun different than the things that are closer? Well, once again, this being your basic science class, we'd start with just this observation. There's a difference, just a complete difference in style. And so what would be the next step in the scientific process after you notice something interesting? Yeah, you create a hypothesis that's based on scientific ideas, that makes testable predictions, and explains why this occurs. Now, some people probably already know the answer, so I'm going to jump to the correct, or when I say correct, I mean the one that we believe today to be the correct answer. And that is, during the formation of the solar system, it was, of course, hotter closer to the sun and colder as you went farther away. That pretty much makes sense, doesn't it? When you're close to the furnace, it's hot. You get farther away, it gets cooler. And so there exists out here a place that they call the frost line. And that frost line is the distance away from the sun where it was cool enough for things other than silicates and iron, essentially, to stick together. That is for them to condense and form a liquid state where they are globbed together. So inside of the frost line, it was too hot for that. And the only things that could stick together were basically your silicates and iron. And so everything that formed inside of the frost line, the only things that stuck together were the silicates and iron, and they're primarily silicates and iron. Whereas beyond the frost line, it was cold enough for other things to stick together, things that had a lower melting temperature. And so then we have things like water could stick together and form clumps and thus be part of the planet. And so that is our scientific understanding. How would you test that? Right? Because the next step is, of course, you have to test the predictions. And so, of course, they go through and they test what happens when we put these gases at different temperatures just to make sure they got that part of the science right. They use modeling for how much energy the sun was giving off in the early stages of the solar system to see how the temperatures compared. And so far, all of the tests check out to support that idea. So that's our understanding on why there's a fundamental difference in the planets. So how did the solar system form? Now, we have in the Bible that it says God created, we have on the first day, God created light. But on the fourth day, God created the greater light to rule the day and the lesser light to rule the night, right? And the stars he created also. So a lot of people take this story, the creation story from Genesis 1, and say that this means that the solar system's formation was all formed as, the sun was complete, the planets were complete, and so on. So a lot of people take that as their, how it originated. To be perfectly honest, there is no way to scientifically differentiate that from the scientist's, explanation that I'm going to give you. That is, if God made it as a mature solar system, then that mature solar system is going to look just like a mature solar system. And so there's no experiment that you can run to say, yes, there's the miracle. So scientists reject, we talked about this with uniformitarianism, they reject something that doesn't involve scientific natural processes. God creating it is not a scientific process, so they say it didn't happen. But there's no test that can rule it out. It's simply a preset, this is a condition I'm going to use to analyze. So taking away the option of a creation, the scientists conclude that the solar system must have formed by having a hot cloud of, a cloud of gas, not a hot cloud actually, a cool cloud of gas that we call a nebula. A nebula is just Latin word for cloud. So we have a cloud of gas. So this picture is showing us what a nebula looks like. Well, what happens to that nebula is you have a shock wave that hits it. Shock wave, a sonic boom is a shock wave. So is the wake. If you go water skiing, the wake behind the boat, that's also a shock wave. It's a different kind of shock wave, but it's the same phenomenon. So a shock wave comes and hits this gas cloud, and when it comes, it makes things get closer together. Now, the gas cloud was a cloud because you had molecules moving around with enough energy that they didn't clump together. Gravity was pulling them together, but their energy kept them from clumping. But with the shock wave, things get closer. And what happens to the force of gravity when things are closer? It gets stronger. And so that stronger force of gravity forced it to then start condensing on its own. So the shock wave started it, and then gravity took over. And if you have something with just a little bit of spin, so if I'm going around a circle with just a little bit of spin, if I pull things in, like pull my arms in, what's going to happen? You spin faster. So the scientists believe that must have happened to the solar nebula. As it started collapsing, it started spinning faster. But as it spins faster, inertia makes it so it tends to flatten out. And so the solar system formed a flat disk. And then we had little clumps that formed besides the center. So the center part becomes the sun. That's just the center. Everything was pulled toward the center by gravity. And so that's where the majority of the material in the solar nebula went. But then you had other clumps that formed farther away. And initially, you had all kinds of those things. So you have the protosun at the center, and then you have little planetesimals that formed all over the place. And those planetesimals, as they smash into things or gather more material, become what we call protoplanets. And as they continue the process, they become planets. But of course, not all planetesimals are going to become planets. Some of them will crash into something else and be absorbed. They'll be assimilated. And so we ended up with 8 big objects and a whole bunch of smaller objects. Now, when I say 8 big objects, I am kind of glossing over things like, Eris. I think Eris is, I would have to check, but I think it's bigger than Mercury. So let's go to our, wait, I haven't hit start yet. Our first clicker question. Of all these things we've been talking about, which ones orbit, that means go around the sun? Waiting for Brittany, Hannah, and Jocelyn. Okay, everybody's answered, and we had 5 people said planets, 0 said comets, 0 said asteroids, and 13 said all. So let's see. Lucky card draw says Valerie. What'd you say?
I said all of the above because I know planets orbit around the sun, and I heard somewhere that comets do as well. I don't know anything about asteroids, so I just wanted to see.
But because you had 2, you said 2 is more than 1, hence it must be all of them. Okay, I did not specifically answer this question, right? I just said the sun dominates, it's most of the mass. But if you go through the story of how scientists believe everything came about, you have everything was out here in this cloud that started condensing. Because the condensing, it starts spinning and flattened out. So everything's spinning around the sun. And in fact, everything should be spinning around the sun in the same direction. And so every single thing in the solar system is orbiting the sun. Comets are orbiting the sun. They're a lot farther from the sun than we are, and because of that, it takes them a lot more time to do an orbit. Obviously, if it's going to be a comet, sometimes it comes closer. if you look at the orbits of the comets, there's the sun. Maybe I should make the orbit first and then put the sun. So the sun's going to become blue now. The sun's like that. So they spend a small amount of their time really close to the sun and a lot of time out here farther away. We have some rules in physics, and one of them is energy can't be created or destroyed. Now, if I have two objects close together, the gravitational potential energy is much, much, much lower than if they're far apart. That is, things fall toward lower gravitational potential energy. So if I start with them fall apart, they'll fall toward each other and speed up. Just like if I take this and drop it, it falls to the ground. So the farther it is away from the sun, the lower its potential energy. But if the total energy, the larger its potential energy, farther away, has more that it can give. But if the potential energy goes up, just like when I brought in the bowling ball, as the potential energy goes up, that is, as the bowling ball came up to my chin, what happened to the speed? It went down because kinetic energy had to drop. So when it is out here, it's very slow because it's far away. And when it's here, it's very fast. So comets may spend only a few months close to the sun and will spend a very, very long time far from the sun, but they're still orbiting around the sun. Okay, so let's talk about each object individually. The sun is a star. So it's the nearest star to Earth. Oftentimes we forget that. And when I say we, I mean we like teachers. We'll ask questions about what's the closest visible star? The answer we expect is Alpha Centauri. But the sun is closer. So the way we try to do it where we're going to be correct is we say, what is the closest visible sun or star to the sun? Well, then you can't answer sun because the sun isn't closest to the sun. The sun is the sun. We could also ask, what's the closest star to the sun? Notice there was a difference in my words there. I started with what's the closest visible star, and that was Alpha Centauri. If I say, what's the closest star to the sun, it's a different answer, although it's actually part of the same complex. It's called Proxima Centauri. Proxima means closer. Proxima Centauri is the proximal star to the sun. That's how it got its name. So the sun is the nearest star to us. How far away is the sun from us? (1.5 times 10 to the 11 meters is a number. That would be 150 billion meters, or just under a billion miles. We have another term for it that makes it a lot easier. It's an astronomical unit. The distance from the Earth to the sun we set as a unit that's very convenient for things in the solar system. We call it an astronomical unit. So one of the questions that often comes up on my astronomy test is, what's the distance from the Earth to the sun? 1 AU. Sorry, I couldn't hear that. I can't even tell who's talking. I'm going to assume it wasn't important. Okay, the sun is composed mostly of hydrogen. How do we know it's mostly hydrogen? Well, first there's theory. Theory says that during the Big Bang, the elements that could be formed were primarily hydrogen and helium, with about 91% of all atoms being hydrogen and about 29-ish% being helium. Or not 29%, 9% being helium. By mass, it's more like 75% of the mass of the universe is hydrogen and 25% is helium. So that prediction from the Big Bang Theory says the sun should be composed of the thing that makes up most of the universe, hydrogen. But we also have direct measurements using spectroscopy. Remember we had a gas tube here and we saw only specific lines that were produced? Well, they look at the absorption of gas by the sun, that is gas in the outer atmosphere of the sun absorbing radiation, and they see there that it's primarily hydrogen. So they do have some measurements there. Now, as you go deeper into the sun, you have more pressure because you have more weight of the atmosphere outside. So the pressure gets bigger and bigger, and the temperature gets hotter and hotter. One of the things that's important to know about the sun is the sun is a miasma of incandescent plasma. I told you we're not going to sing. I almost did, but that's the follow-up to the sun is a mass of incandescent gas. Incandescent means it's giving off light because it's really hot. Plasma means an ionized gas. That means you yanked an electron off. If you yank an electron off of a hydrogen, what do you have left? What's a hydrogen atom made of? One proton and one electron. So if you take the electron away, you're left with one proton. So the sun is essentially just protons flying around. Now, as you get deeper in the sun, you have electrons as well, but they're not attached to the protons. So you have electrons flying around, you have protons flying around. You get deeper in the sun where the pressure is really high, and it actually forms a metallic form of hydrogen. And scientists have been able to make liquid hydrogen on Earth. It started, when I started teaching, liquid hydrogen was theoretical only. They theorized the pressure was so high that it would make a liquid metal hydrogen in the sun. But now they've been able to actually do that on Earth, giving them more confidence in that prediction. Why is that metallic hydrogen important? Well, the sun has a very strong magnetic field. What makes the Earth's magnetic field, we believe? It is the iron in the liquid core swirling around, also with convection. You have to have a conductor swirling around to make the magnetic field. Well, the sun, with its very strong magnetic field, has to have a conductor swirling around. They believe that it's the liquid metallic hydrogen. Of course, it could be just ionized hydrogen. Who cares? You go in deeper. Actually, yeah, I got to think about this. Is it? No, it doesn't form liquid metallic hydrogen in the sun. It's Jupiter. Wow, that's embarrassing, especially because I post these on YouTube and every now and then somebody listens to it. I had somebody who put a comment saying I was wrong and I wasn't, but when I tried to reply, they'd taken away their comment, so I couldn't tell them they were wrong in saying that I was wrong. Well, there I would have been wrong. It's not liquid metallic hydrogen in the sun because, of course, they're ionized. They're just protons. It's in Jupiter that you have the liquid metallic, and Saturn. Okay, the hydrogen is fused to helium in the core of the sun. So just like the Earth has a core, the sun has a core, it's just the place in the center. The temperature and pressures there are super high. In order for fusion to occur, fusion is where you have two protons, in this case, hydrogen fusion, two protons that come together and they are forced to get so close together that the force that attracts them holds them together. Now, I say the force that attracts them holds them together. And you used to be saying, how can they attract? Because two protons should repel. We have the electric force that says like charges repel. That's why you have to have a high temperature to make them come together, because you have that repulsive force. But scientists have learned that there are two additional forces that only work on very short ranges that affect things like protons and neutrons. And it's always attractive. So protons are always attracted to other protons, but you have to get them really close for this force to become sizable. And so you have to have it really hot so you have enough kinetic energy for them to actually come and get close enough for that force to hold them together. So you can think of it kind of like if you had two positively charged ping pong balls with Velcro. If you get them close but not close enough for the Velcro to touch, they'll just push each other apart. But if you get them close enough for the Velcro to actually touch, then you'll have something to hold them together. And that's what's going on in the nuclear fusion in the sun. But when they stick together, it's lower energy, that's why they stick, and it releases the excess energy that gives us the energy coming from the sun. Now, this hypothesis about the sun fusing hydrogen to helium makes testable predictions. One of those is that when you have the reaction, you should have for the net reaction 4 hydrogens come together and they produce a helium-4 plus, and I think it's I think it's 4 electron antineutrinos and 4 electrons. No, not 4, 2. I think that's the net reaction. I did not look this up beforehand. But in that reaction, you are releasing these electrons and neutrinos. Neutrinos are little itty-bitty particles with extremely small mass and no charge. Now, if I have no charge, if I bring it next to a nucleus with a positive charge, how's it going to interact? It won't. If it's neutral, it won't. So that means you don't have any charge interactions. If its mass is really tiny, it's going to have virtually no gravitational interactions. So these neutrinos travel really, really fast, like 99% the speed of light, and basically don't interact with anything. So as you sit here, clicking away in class, you are being flooded with neutrinos right now from the sun, is what the theory says. And those neutrinos are just going through your body, which sounds scary, except for they're just going through and they're not interacting with you. They just go right through us. So that's something they said there should be these neutrinos coming through and going through the Earth. So how do we know that they're there? Well, you can make some unlikely observations. You can make a big tank and fill it with water, and there's a very, very low chance that one of those neutrinos will interact with a molecule and produce a flash of light because of the interaction. And so then they did that. They essentially took old mines, filled them with water or dry, clean solution, and then they put little detectors all around to detect the flashes of light in these underground mines. And they measured how many neutrinos they saw. Now, this is something that could confirm or disprove the idea that the sun is fusing hydrogen to helium in its core. Well, they found neutrinos. They found about 1/3 as many as predicted by the hypothesis. So what do you do if you have an experiment that does not agree with the hypothesis? Yeah, you got to go back and modify things. So scientists were like really concerned, like, it seems so good. Well, it turns out, yes. Okay, it turns out that there are 3 fundamental types of neutrinos, and the sun is only producing one of those 3 types. And the neutrinos, and this was discovered once again after I started teaching within your lifetimes. Of course, within your life. Yeah, it wasn't discovered before you were born, unless, of course, you're less than about 18. They discovered that the 3 types, they have some mass and they can change from one type to the other. And they're only measuring one type because they're measuring the type that's created in the sun. But the ones that are creating the sun could have changed to the others, and statistically, by the time they get to the Earth, it should be 1/3 of each type. And so the fact that they only measured 1/3 as many as predicted turns out to be, with a better understanding of neutrino, exactly what the theory predicted. So, did they have to change the theory? Their hypothesis? Yes, they did, because they had to change it because their understanding of the neutrinos was not good enough. But then when they found, with understanding neutrinos better, the observation perfectly matches the prediction, then that gave them an extra joy, wow, there really must be something to this because we thought we were wrong, but it turns out we weren't. That's, by the way, an important lesson to learn about scientific experiments to begin with. When you make an experiment, you want to make sure you keep your data. You don't just say, oh, that's bad data and throw it out, right? They had this data, they observed things, they tested, and then after studying, they realized, and this was like a decade later, that data was actually what we should have predicted if we had understood things correctly. And so the data suddenly became very important. And, I was told that in my research lab before I arrived, there was a guy, anytime he had data that didn't support his hypothesis, he would just write bad data and destroy it. And that's not scientific process. Okay, of the sun's energy that it releases, only a tiny fraction gets to the earth because it's going out in all directions and we're just a little speck as viewed from the sun. So most of its energy is not coming to the earth. Yet, it's more than 99% of the earth's energy budget. That is, of the energy we have, solar energy, obviously that comes from the sun. But as we learned in the last chapter, so does the wind energy, right? Because that's driven by the heating from the sun. And even things like the fossil fuels, where the fossil fuels come from, ultimately you had things that were eating vegetation or vegetation itself that then got compressed and transformed into oil. So virtually all of our energy comes from the sun. The small fraction that doesn't comes from nuclear energy in the earth. Okay. The sun, I'm sorry, it thinks that I want to install something now. The sun is releasing energy to us. Strictly speaking, what's happening to the sun's mass as it's releasing energy to us and everything else in the solar system? Strictly.
It's supposed to be a hit.
Well, it's kind of. Obviously, I'll explain this after everybody's answered. The question is to light the curiosity fires in your head. Waiting for 2 more. Just 1 more. There we go. Okay, the answers we got were pretty spread out. 9, 3, 1, 5. Okay, so I'm not calling on somebody on this one because this was, again, something that was more to get you thinking, not one that we've already studied. We know that the sun is giving off energy. So what's happening to the energy of the sun? It's decreasing, right? Because we can't make or destroy energy. Well, where is the sun's energy coming from? I said that it's doing what? Fusing hydrogen into helium. And so we have the hydrogen fusing into helium. How is that going to release energy? Well, Einstein gave us an equation. He said that mass is just a form of energy. E is equal to mc squared says that everything has energy. So this water bottle, if I take the mass of this water bottle and multiply it by the speed of light squared, now what's the mass of this water bottle? I don't know, maybe 0.1 kilograms. I multiply that by the speed of light squared. That's 3 times 10 to the 8 squared, or 9 times 10 to the 16. 0.1 times 9 times 10 to the 16 is 9 times 10 to the 15 joules of energy. Now, 9 times 10 to the 15 joules of energy is enough energy to keep Union College going for at least a year. So we have enough energy in the form of mass right here to keep college going for, I said at least a year because I didn't want to sit down and do calculations, but a very long time. That's what Einstein said. Of course, we have to figure out how to use that energy, how to make it release from mass form to something else. Fusion and fission are 2 ways of doing that. Can't do it on the same thing. And so as energy is released, this mass is being converted into solar energy. And so the mass is dropping, so the energy can be released. The fact is the mass of a helium atom plus the neutrino and electrons is smaller than the mass of the 4 hydrogens that you started with. And so it's constantly losing mass due to this fusion. Now there's another process that's much bigger. It's also constantly blowing away protons. And so it's also losing mass that way. But we hadn't discussed that, so you didn't have any ability to answer based on that action. So it's losing mass 2 ways, converting mass into energy and blowing it away. Now looking at the inner planets, the ones that have the high density rock, they're all going around the sun, and as you get farther from the sun, the speed of its orbit gets smaller. Talking about them individually, Mercury, the closest one to the sun. Mercury is slightly larger than the moon. It's very similar to the moon. In fact, when you look at Mercury, it really looks a lot like the moon. It has some features that the moon doesn't have. It has like these scarps that cut through it. It has a high density. They actually believe that it lost a lot of its outer portion. It has almost no atmosphere. It has a small size. What does that tell you about its gravity? Not very much. Because it doesn't have much gravity, it can't hold on to atmosphere very well. Furthermore, the sun is nearby. The sun is hot. And so on the side of Mercury that's close to the sun, it gets really hot. Notice there, daytime is long and hot, up to 430 degrees Celsius. So any gas molecules on that side are going to be very hot, which means they're going to go really fast, which means it's going to be even harder for Mercury to hold on to it. There is some evidence that Mercury may be able to hold on to a transitory atmosphere for about 2 weeks. What does a transitory atmosphere mean? It means that basically hydrogen atoms flying at it from the sun may be trapped for a couple weeks before they escape. So it has no permanent atmosphere and very, very, very thin atmosphere for what there is, and that atmosphere is going to be on sides that are not sunlit. The nighttime, very cold. Very different temperatures between day and night. This is an important function of atmosphere. Atmosphere helps to transport the energy around to keep the temperatures from going super hot to super cold. Well, Mercury with no atmosphere, on the side that's not getting any sunlight, there's nothing heating it. It doesn't have bodies of water with their high specific heat, so it rapidly cools and gets very cold on the side that's not lit by the sun. The side that's lit by the sun, once again, not having water, it just heats up really quickly, gets really hot. Not having atmosphere, you have nothing to spread that energy around the planet. There are some other things about Mercury that I have to say just because it's so totally cool. Mercury has the most eccentric orbit. Let's say that you were to tell somebody, yes, my teacher is very eccentric. What would you be saying about that teacher? They're odd. In math, when we talk about the orbits, we have the orbits are ellipses. Ellipses are like circles that have been stretched. And the eccentricity tells you how stretched it is. So the eccentricity tells you how odd of a circle it is. So Mercury has a fairly eccentric orbit. That means when it goes around the sun, its orbit is something like that. That does not look like a circle, right? It's an odd circle. And so you have the sun is somewhere like here. And of course, these shapes aren't perfect. Just notice the sun's not at the center. And so Mercury is going to go faster when it's closer to the sun, slower when it's farther away. And because of that, you have a difference in how long a day will be depending on where you are. But things get more interesting. We have what we call tidal forces. That is, gravity is stronger on things that are closer, weaker on things that are farther. And that has caused some interesting things, like the moon is tidally locked with the Earth. The moon always has the same side of the Earth facing us. Did you know that? Okay. Now, it's not perfect because the moon's orbit around the Earth is not a perfect circle. Because it's not a perfect circle, depending on where it is, if it's closer, it's going a little faster, and you actually have a little bit of variation in the face you're seeing of the moon, but it's changing about like that, so you don't notice it. But you can take pictures that are taken over a month, and you'll see that slight variation. Well, because of the more eccentric orbit of Mercury around the sun, it tried to set up a tidal locking. So one side was always facing the sun, but because of that eccentricity, you have much bigger distance differences. And it turns out that when it does one complete orbit, it will have done 1.5 rotations. 2 complete orbits, 3 rotations. Well, 3 rotations, yes. And so it's in a 2 to 3 orbital resonance, which is really weird. It makes its days something like 59 days long, and its year is 80 some days long. So its day is a significant fraction of its year because of that tidal locking. Next comes Venus. Venus is called the Earth's twin because it's about 95% of the size of the Earth. But of course, the weather on Venus is very different than the weather on Earth. You had a homework question, would there still be weather if we didn't have any water on Earth? Is there weather on Venus? Yes. Is there water on Venus? No. Right, so there's an example. Yes, there would be weather. But what do you have going on in Venus? First of all, Venus has a very thick atmosphere. Its atmosphere is about 90 times as thick as our atmosphere. And the gases are, I believe it's acidic. They're pretty costly. It's largely carbon dioxide. Ooh, carbon dioxide is a greenhouse gas. It's the one that man contributes to on Earth, right? Of course, water is the dominant greenhouse gas on Earth. But it has what we call a runaway greenhouse effect. The greenhouse effect is very strong, which means you have solar radiation gets through the atmosphere in, the radiation given off by the planet gets absorbed by the atmosphere and locked in. And so the temperature has gone up and up until it's reached an equilibrium at about 800 degrees Celsius. I think it's Celsius. Hope it's not Kelvin. I should have gone through these numbers in preparation. It's super hot. Because it has a thick atmosphere, how do you suppose the temperature varies from one side to the other side? Not very much. It's pretty much the same temperature everywhere because that atmosphere is locking in the heat and transferring it around the planet. So no matter where you are, it's very hot. How do we know anything about Venus? The Russians have sent spacecraft that have stayed there for up to 90 minutes before being destroyed by the high temperatures and chemical conditions. So we do have some limited pictures from the surface of Venus. Otherwise, we can have satellites orbiting it and use radar mapping that goes through the clouds and can map the surface. So we have some reasonable information about Venus. Too hot, we can't live there. Theory is that it never got the right temperature for liquid water to form on the surface, that it should have had about the same amount of water as the Earth did, but never got the right temperature for it to form a liquid. Hence, it never encapsulated carbon dioxide into rock and was, because of the high temperatures, the water basically got baked out, and you got that. Now, habitable zones. We live on this Earth. Could we live on Venus? No. Is it possible for something to be done to Venus to make it so it would be habitable? And by something done, I'm not saying do we have the technology to do it, but there are things that can be done. If you look at this graph, it marks in green the range of orbits that would produce habitable environments under the right conditions. And you can see the Earth is in the inner edge of that habitable zone, and Mars is in the outer edge. Venus is not in the Goldilocks zone, the habitable zone. But Mars is. So maybe, just maybe, we could get life on Mars. Hence, we spend a lot of money looking for life on Mars. So Mars, it's a small planet compared to the Earth. It says a little more than half the Earth's size. I think it's more like 3/4 the Earth's size. But once again, I didn't look up the numbers before the lecture. It has a very thin atmosphere. Its atmosphere is about 1% the Earth's atmosphere, which means that even if it was 100% oxygen, you couldn't breathe. You wouldn't have enough oxygen. But it's 95% carbon dioxide and only 0.15% oxygen. So you're even more in trouble. But if there was a way to produce an atmosphere and get that atmosphere thick enough, then we could live on Mars. And so people spent a lot of time and energy figuring out, okay, could we introduce some kind of plant life that would produce an oxygen atmosphere? Now on Earth, we talked in the last section about very important stage in the Precambrian where oxygen was produced. And how did it say oxygen was produced? Photosynthesis by plants. Now, when we say plants, we probably need to back off a little bit. Initially, it was just bacteria, right? It said the stromatolites were really important for their production of oxygen gas. So people have tried to theorize now, what kind of bacteria might we be able to introduce to Mars that would produce more oxygen in the atmosphere? And then when you have more oxygen, you might introduce another type that would be more efficient to build up enough oxygen to have an atmosphere that's thick enough and has high enough oxygen content for us to breathe. So it is an area where people do a lot of research trying to figure out how we can make it habitable. Why would they want to be habitable? Well, we look at our Earth and we know, as Mr. Winterberg used to say, sin is everywhere. And as the Bible says, knowledge increases, men to run to and fro. From my perspective, I believe life here is doomed. In the end, Christ is going to come, etc. But if you don't believe Christ is going to come, you're like, well, what are the options here? We could A, have a big nuclear war. One of my friends thinks that might be this week because of North Korea thing. We might have a nuclear war, in which case Earth becomes largely uninhabitable. Well, what do we do then? If Earth's not habitable, we want our species to survive, so we need to find a way to, live on a neighbor like Mars. Or the other side of the coin is, what if we don't destroy each other? Then what happens? Our population is going like this. Too much population, we start having starvation, blah, blah, blah. And so we need to send people off elsewhere so they can, not be starved and choked out. So there's reasons why people care about these things. Notice the temperatures on Mars. A hot day will get up to 30 degrees Celsius. Cold or warm? Warm. The classroom here is about 20 degrees Celsius. On a hot day, we might get up to 40 degrees Celsius. So 30 degrees Celsius is, it's somewhere in the 80s. Negative 130 on the other hand, that is decidedly cold.
So
the cold temperature is not livable to us, but the high temperature is perfect for us. And so if you could get some atmosphere to equalize the temperatures and keep from getting cold, you might have a nice, 68 every day, like, where I grew up in Monterey Bay Academy. Question, Brandon.
Do any other planets have seasons? Like, are any of them tilted?
Okay, great question. Especially notice he added the second piece to it. Are they tilted? Do they have seasons? Are they tilted? The answer is yes. Now, there's some really interesting, I'm going to end with this, some really interesting things about those tilts. Venus, it's spinning backward really, really slowly. Its tilt is close to 90 or 180 degrees. It's like 170 something. So it has very small seasons because that net tilt is a small angle. Mars is tilted in a very similar angle to us, so it has very similar seasons. And Uranus is on its side, so it's spinning like this as it orbits around this way. And so it has an 84-year orbit. And basically, unless you're at the equator, you spend 42 years in summer, 42 years in winter. And you're going to have the most extreme possible winters and summers. You know, if you're at the pole, you're going to be facing straight at the sun for a while. Okay, have a great day. I'll see you on Wednesday.